Good afternoon, and thank you for joining us on our call today. We're going to get started in just another minute. Okay, it is 2 o'clock, so we're going to get started. Good afternoon. Thank you for joining us. My name is Nicole Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic today is IR thermometers versus IR cameras, eliminating the guesswork. The topic is being presented by Ed Kochanek with FLIR. Ed has been with FLIR for over 17 years, both as a district sales manager and now as a director of sales for the Eastern region. Ed has a level 1 certification from the Infrared Training Institute, and he has also done many infrared training classes across the country for major electric utilities and groups such as the NC State Meter School and Doble's Circuit Break class. We expect today's presentation to last roughly 30 to 40 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that the webinar is going to be recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I am going to turn the presentation over to Ed.
Good afternoon, everybody, and thank you, Nicole. It's a pleasure to be here as we talk about thermal imaging cameras, infrared cameras, and how they can be utilized as an alternative to IR spot guns. When I started in this business over 17 years ago, the average price of a thermal camera was around $56,000. And the average manufacturing plant or customer, that was beyond their affordable means to invest in this technology. So they would hire out consultants, or if they were large enough, get their own. But of course, they would take it right to their electrical rooms, their utilities, and basically just do the most critical parts of their plants because the cameras were very expensive, complicated, hard to use, and they only trusted their very best employees at that time with that technology. And as we see this individual overlooking his manufacturing floor, while he recognized the value of the IR camera, he was also responsible for all the maintenance of the rest of the plant. And he would thereby have to basically use a crystal ball to figure out what would fail next. He knew an infrared camera would be a great device to help him find all his electrical problems. Well, what about the other problems within the plant? Or what about the medium voltage problems in the plant? So if he had to rely on those, he would have been better off with something as basic as a magic 8-ball, something, you know, just taking a wild guess at his problems. But what we know is that when things go bad, they heat up. And I show this clock on the wall on my presentation to indicate that as a society, we measure time all the time. We have it on our smartphones, we have it on watches, we have a clock in our car. Wherever we go, we measure time. Do you know what the second most measured parameter is? I'll let you think about that for 1 second. What could possibly be the second most measured parameter that we measure every single day, almost routinely, as often as time? It's temperature. And temperature is a great indication of the performance of our equipment. Even when you listen to the news radio, they always do time and temperature together. Not only does your car have a clock in it, it has a temperature meter, and it also has a temperature meter on your engine as well. When your body gets sick, you take your temperature. And that is true of every piece of equipment. When things go bad, they heat up. And when I started in this business and cameras were selling for $56,000 and then $25,000 and then $10,000, everyone recognized it would be valuable to have a device that can do non-contact temperature measurement. A rhetorical question to the group right now would be, how many of you have or have used a spot temperature gun within the last year? My guess is quite a number. Why? Because they're affordable. They range in price from $50 to $150 for basic temperature measurement, and even some fancy ones go up to $1,500 if you're really looking at some high temperature targets. But this is the technology that has proliferated through most industries as the low-cost alternative to infrared cameras. So the point of this part of this presentation will be going over how these devices basically fool you into believing the temperature measurement they are giving. So this part of the presentation is the replacement of old, inefficient, and ineffective technology, the spot gun versus the thermal imaging camera. And just to note a disclaimer, one of the brands that I showed already is made by X-Tech, a company that I represent as well. So I'm not picking on a manufacturer. I'm just showing you the value of a thermal camera over a temperature measurement device that my company makes as well. And why is there a conversion to thermal imaging cameras? Five reasons: speed, accuracy, documentation, safety, and finally, affordability. So a spot gun works on the same physics of an infrared camera. It just has one detector. And that detector gives off a temperature measurement on the screen. So here we're looking at this example, the spot gun's detector is measuring 175. That's what the spot gun's going to tell you. But an infrared camera, depending on the type of infrared camera and how many pixels, like we're looking at with this camera has 19,600 pixels. That's equivalent to having an array size of 19,600 spot guns. We know that's not practical, but that's actually the true measure of the two devices, that a spot gun giving you one measurement point, where an infrared camera, and it's in this case, could give you 19,600 measurement points. And there are infrared cameras that go over 1 million points of measurement. So we are closely following the visual camera world and number of pixels we can create or temperature sensors on an image. The other benefit is speed. How quickly can I find a problem with the thermal imaging camera versus a spot gun? So in this example, if I'm looking at this circuit and I was using a spot gun, I'd have to measure this component a minimum of 9 times. I am looking for the delta between A, B, and C phase across the two connections in the body of the fuses. That equals 9 times. In comparison, a thermal camera only has to look at it once. So if you had to look at 9 different circuits, that's 81 different measurements, with the most of the measurements being probably not a problem. There wouldn't be a problem there. With a thermal camera, on the other hand, a picture's worth 1,000 words. I clearly see, in this case, C phase is warmer than A and B. So from that instant, I would then take more additional information that the camera can provide me. We can easily see not only the temperature of the 2 points, but also the delta that we would have here is roughly 18 degrees. There are many building applications that we will get to later on in the presentation. If I was looking at this example, I'd have to scan up and down very tediously to see if there was a problem, where with an infrared picture, I can clearly see if there is a problem. As in this case, this 5-ton, 8-section coil has a flow restriction, and I can see a thermal hotspot across the middle of it and in the upper 80% of it. We're now going to talk about accuracy. Now, everyone who's had a spot gun, hopefully you've looked on the side of it, because on the side of it, the spot gun tells you its spot size ratio. Now, the problem with a spot size ratio is it's hard to understand what that practically means. So if you have a 12-to-1 spot size and you are 4 feet away or 48 inches away, your measurement area is 4 inches. Now, that may not seem like a big number, but trust me, it is when you start looking at your targets. So with these fuses, if I use a spot gun, I'm going to get a 90-degree temperature measurement. And the reason why is because I am looking at this picture, and if you see the 3 temperature measurements of 175, 75 degrees, 85 degrees, and 145 degrees, you are averaging all those temperatures. So the spot gun has no ability to identify the hottest pixel because it's just 1 pixel, and that all becomes an average. So if you look at a lot of your circuit breakers and your fuses, if you're 4 feet away and you have a 12-to-1 spot size ratio, your diameter of measurement is 4 inches. If you go back further to 5 feet, it's 5 inches. Now look at the sample area that you're trying to measure. It's much smaller than that. If I use an infrared camera and I overlay my focal plane array, the grid right here, you can see clearly one of those pixels is identified on top of the hotspot. I'm not averaging the rest of the cool areas. I'm able to get an accurate measurement of 145 degrees. That is a dramatic difference. That is almost 55-degree difference between an infrared camera and a spot temperature gun. That is the difference of seeing a problem and missing a problem. The next value of an infrared camera or thermal imaging camera is documentation. With a spot gun, basically there is none. You have to write it down and have to hope that your handwriting is legible when you go ahead and tell somebody that there was a problem. With an infrared camera, you not only get a 2-dimensional picture when you take the picture, but you can bring it into the free software that comes with the camera that will allow you to create reports. Many thermal cameras out there both take a thermal image and a visual image, as we can see these 2 images side by side. The value is it gives a complete description of what's hot and what could possibly cause the problem. In software, we also have the ability to analyze more than just the 1 pixel that we were looking at before. We can measure all the pixels. We can adjust the contrast and brightness. As long as we have the picture in focus when you took the picture, you can analyze it after the fact and change palettes, change measurement spots, and you can help build the return on investment and reporting for either your customers or your managers if you had to repair a problem you discovered with the thermal camera. Safety is another big topic with a thermal camera. Here is a picture of an electrician. He is suited up in his PPE. In his left hand is a clamp meter. To measure the load or voltage of an application, it has to be energized. With regards to safety, he should be wearing his PPE. That is like wearing seatbelts in a car. If there's an arc flash and you have your PPE on it, you should be able to survive it, just like if you were in a car crash and you had your seatbelts on. The problem is, without an infrared camera, that operator is working in the dark. So if I continue the analogy, an infrared camera is like headlights. Even though you're wearing your seatbelts in a car, you would never drive your car at night without your headlights. Well, due to the affordability of thermal imaging cameras, you now get to see the hot spots that you're about to clamp on before you do that. So in this example, I show a termination failure that the previous picture of the operator would not have known if he did not have an affordable camera. If he moved that wire to get the clamp meter around it, he may cause the connection to have an arc flash because it is very close to melting down. I've blocked out the temperature because this target is very close to the melt temperature of aluminum. Does anybody know the melt temperature of aluminum? It's around 1200 degrees. In this case, this target is around 1076 degrees. That's why electricians are guided to wear PPE, but I would suggest the next step level up would be to also include a thermal imaging camera that can show you this problem before it happens. And finally, thermal cameras are affordable. We'll talk more after this presentation and after Q&A for those that wish to stay on, but the price of thermal cameras has gotten down below $400 now. So when I look upon this gentleman again, I think about all the applications and him having to use either his magic 8-ball or his crystal ball to see what his problems are. The opportunities within the plant have now expanded to every electrical connection, every mechanical connection, and even the building envelope, from the roof to the walls to the HVAC system. And the next slides will go through some of these applications. Before we get there, I'd like to talk a little bit about what infrared is. Infrared's part of the electromagnetic spectrum. Our eyes cut off at a certain wavelength. From 0.4 to 0.7 microns, that is the pitch of the wavelength that our eyes see. After that are the infrared bands. There's the mid-wave band from 3 to 5 and the long wave band from 8 to actually 13. Our cameras, 99% of all thermal cameras operate in the long wave bands. And after infrared becomes microwave. And that's a bandwidth we're all used to seeing because those bands, those microwaves, are actually bigger than the holes in your microwave oven when you look inside to see how your food is doing. Infrared is smaller than the holes in the microwave oven, so infrared radiation can pass through. Since infrared waves are emitted by all objects, infrared also increases with temperature. So if you're a cold target, we can see it with an infrared camera, as well as if you're a hot target. And in certain situations, like we'll see later, cold is an indication of a problem as well. So let's talk about electrical applications first. In this example, the main conductor overheated to more than 220 degrees with only a nominal load. One of the things we know right out of the gate is that when there's an infrared problem or there's a hot spot on your target, it's always best to know the load, because the load would indicate how hot that target is at the moment or could have been. A faulty conclusion would be that target is measuring at 220 degrees and that's the hottest it's ever been. Because if it was at lightly loaded at that time, if someone applied more load to the application, that temperature would skyrocket exponentially. And the hotter the target also changes the way you repair things. It's good to know the tensile strength of your metals, so if something got so hot, clean and tighten is not the best response. You might have to disassemble it and put it back together again with new components, because if it got too hot, you might lose the tensile strength of your materials, thereby ensuring once you fixed it, you'd have to go back and fix it again after it loosened up. Many infrared applications are as simple as what doesn't belong. Here, B phase does not belong versus A and C. It's that simple. B phase sticks out sort of like a sore thumb. And then I can measure the differences between B and A and C. Provided that the loads are all exactly the same, that would indicate that there is probably a loose connection here. And depending on the temperature, depends on your corrective action. Sometimes applications can be, you can figure out that there's an unbalanced load. Or here with fuses, I can see A phase is 166 and B phase is 129. So that is a 37-degree temperature rise. Depending on the criticality of your system, you may choose to fix it now or determine that I can run this for a little bit while longer, get the parts in, and then fix it at my convenience. That is the beauty of infrared. It allows you to defeat Murphy's Law, that common expression, when things go bad, they go bad at the wrong time. When things go bad, they didn't go bad immediately. They've been going bad for quite some time. All problems don't go from being fine to bad in an instant. It's a gradual time. So by using thermal imaging, you'll be able to find these problems before they become critical and cause a plant fire. I even recommend to our customers, look outdoors. Look at the electrical utilities that feed your facility. If you find a hot spot there, that can cause an outage for your building. Let your utilities know as well that they have a hot spot near your location. If you use batteries, an uninterruptible power source, here we see a 120-degree temp rise on a battery that is not giving off any power or supplying load to the facility. This is under very light load. If there was an outage and this battery power supply had to kick on, there's a good chance that this would explode, because once load was placed on the system, that 120-degree rise would skyrocket exponentially. Many applications and many facilities can be also looked at bus ducts. This is what we would call an indirect temperature measurement. There's heating on one part of the on the bus duct versus the other side of it. That's 16 degrees. Anecdotal evidence indicates and tells us that that rise is probably 20 times that temperature difference. And when that part fails, if you are familiar with bus duct fires, you know they can be quite explosive. Motors are a good source for heat. Infrared is a complementary technology to vibration. If you do any vibration analysis, there's a pretty good chance you already have an infrared camera. In this case, 18-degree Fahrenheit over on the outside of the motor. Every motor has a faceplate on it, and on the faceplate has a internal temperature rating. If we are 18 degrees above that internal temperature rating on the outside, you are going to cut the life cycle of that motor in half. So in this case, you are running this motor well beyond its thermal rating. Infrared's really good at motors that are hard to reach, hard to get, stuck in the air. The bearings on motors are a very good target as well. So here we see a motor on an air handling machine, and the belts and the sheave that are underneath the guard are probably causing an overhung load condition, thereby exerting friction on the bearings. That is resulting in heat of an 8-degree temperature rise. The bearing ring should be no different. There should be no difference in temperature around the shaft. It should be all about 116 degrees there. The fact that you see that indicates that there's a problem. When looking at bearings, it's good to compare like versus like, meaning manufacturer, and also doing the same exact work. So in both these cases, the bearings are made by the same manufacturer and doing the same amount of work, except one on the left is showing a 35-degree temperature rise, and the one on the right is showing a 25-degree temperature rise. They should be the same temperature. Here's a simple example of how infrared can help maintain the productivity of a plant. We see this conveyor system. That's an idler bearing. It's a $5 thrust bearing on an idler supporting a belt conveyor. The most expensive part of the belt conveyor is the belt. That could eventually fail, turn into a pizza cutter, and now chew up potentially your $100 a foot belt. So even the smallest part within a facility can cause catastrophic damage and cost. It's never been so true that you're only as good as your weakest link. You can use an infrared camera to find those weak links. So here's a classic example. The invisible. We make the invisible visible at FLIR. So I have these two motors, these two spindles right here. With our eyes, we can't see any difference. Maybe one appears to be a little dirtier than the other. But under infrared, we see the one is much warmer than the others by roughly 20 degrees. They're doing the same amount of work. They should be the same exact temperature. But we discovered that the one on the top is about 20-degree difference. When we opened it up, we could see the scores and the brunelling on the bearings on the left-hand side of this picture. If you look at the left-hand side compared to the right-hand side, you can see the much smoother thrust bearing. Once we installed the thrust bearing, the motors returned back to the same temperature, thereby avoiding a catastrophic failure. That is simple return on investment 101. So now we're going to jump over to some HVAC and building applications. Here's an example of a miswired fan motor. We're seeing excessive heat on the picture on the right to more than 220 degrees. If you used a spot gun, there was a pretty good chance you would have missed this. And by my ability to store a picture, I can show my client the picture And our clients tend to believe with our eyes, not with our ears. So now you can not only describe the problem, but you can show it. Here, the customer, the thermal imaging camera user detected a freon leak under pressure. We see this small little cold spot in the lower right-hand corner in the thermal image. Here's an example of an overcharged system. On a return air intake, the lower half of the evaporator coil is below freezing. With infrared, you are looking for anomalies. I would have expected to see a consistency across this target. The lower half is very, very cold. Here's an example where a customer got blown in insulation in their office. It overhung the factory floor. In the summer, it was too hot. In the winter, it was too cold. So he didn't want the heater or the air conditioner running full time. He figured, let me insulate. Unfortunately, the contractor did every other stud bay. So where you see the purple, the cold, is where they are missing the insulation. Needless to say, the customer was not happy because he paid the contractor to do the entire job. Here's another example of blown-in insulation. We can see the window on the left. You can see the studs in the wall on the right. And you can see the uneven pattern where it's purple versus yellow-orange. The yellow-orange is the insulation. The purple is the gaps they're missing it in. So if the job wasn't done correctly, that's the type of picture you're going to see. This is another classic picture. Companies may overrun their heating and air conditioning because the thermostat was put in the wrong position. So this thermostat is been put in an uninsulated portion of the wall. So the right side is red where there's insulation. The left side of the stud and the nail pop that you can see there, that's where it's exposed outdoors. So the customer is not getting the right internal temperature to set his HVAC equipment. This happens all the time. If you can create negative pressure within your building, you can see air infiltration and where you need to do additional sealing and insulation like we do here on this drop stairwell. People like to use infrared cameras for their energy efficiency of their windows. Windows tend to be a bit of a challenge. They're very reflective. In this case, they put the window in backwards. If you have and you want to use an infrared camera to see where the insulating gas argon that is used in high efficiency windows as a insulation gas has leaked out, this is the pattern you will see where you see the three hot spots or a hot spot on the window. That's an indication that it's lost its E rating. If you're in a manufacturing plant and you wanted to see if there was leaking in your piping system, here is an example of a condensate leaking into an insulated pipe. We can see the hot spot The green circle is identifying that, and you can see the water and saturated insulation underneath the metal cladding right there. Companies like to use our cameras in steam traps. Again, an infrared camera is a second tool to ultrasound for finding steam trap problems, but it can be used to help identify certain problems within steam traps. I started this discussion identifying the spot temperature gun as a device used for temperature measurement. Infrared cameras are also used to find water within buildings. So another tool that someone can use to detect water is a moisture meter. In certain respects, the moisture meter suffers the same time issues as a spot gun. It takes a very long time to use a moisture meter to find water on a wall, in a ceiling, on floors. An infrared camera is going to show water very easily. Why? Due to evaporative cooling. When water goes from a liquid to a vapor, it's cooling the target that it's on, in this case the wallboard, and it shows it up as a cold area. The only difference is you still need the moisture meter to confirm that it's wet. So for example, this customer complained of leaking on the first floor. They used the infrared camera to see where the water was coming from. It was actually coming from the third floor. So the second floor did not cause the leak. It was coming from the third floor, as we can see the cold spot along the vinyl siding. I get this question all the time. Will an infrared camera see mold? It will not. An infrared camera cannot detect mold. What it can detect is the presence of water, as we just described. So in this, you can see the ceiling tiles, the cold, dark spots is water that's evaporating. Here's another example of water on a ceiling. If you look closely, under the FLIR logo in the upper left-hand corner, you see this yellow stripe. That is the ceiling joist between the first floor and second floor. But we can clearly see where there's water in this picture. Many customers use our cameras for concrete block construction. If you wanted to see if they've reinforced the walls while they're doing manufacturing, as we can see here, the customer put the support structure up only 2/3 of the way. So on the left-hand picture, those white stripes should be going all the way to the top. Here's a similar example. This customer is missing reinforcement in the hurricane zone. You can see in the right-hand picture the cold areas where there's reinforcement, and along that window, while there's no indication in the visual light picture, in the thermal picture, we clearly show it's missing its supporting structure. And finally, a very popular use for a thermal imaging camera is for rooftop moisture. Now, rooftop moisture is the one application that's pretty much dependent on the environment when you're outdoors. If you were worried about roof leaks in your facility, you can use an infrared camera to find where they originate from on the roof. You wait for a nice warm day where there's no water on the roof. The water will be saturated inside the insulation, but the roof is completely dry on top. After the sun goes down, you get up on the roof and you start looking for hot spots on the roof. The reason why you would see a hot spot is during the day, the sun's going to warm the roof up to a nice hot temperature. In the evening, we are going to have heat transfer where the roof releases its energy to the sky. So the dry roof will cool rapidly. The wet roof will cool slowly. So you have about a 5 to 6 hour window to see if there's any hot spots on top of the roof. If you find them, that's a pretty good indication of where the water is. You come back in the morning, you do a core test, you verify if there's water there, you found your roof leak. So in summary, IR cameras provide the whole picture for electrical maintenance, mechanical maintenance, water discovery, energy loss, and building construction. Nicole, are there any questions?
Hi, Ed. Yep. I just had to unmute myself. I did see a couple questions. Let me see if I can pull this out.
And while Nicole's looking for it, if you guys want to type in a question, you can. At the end of the questioning period, we're going to end the official webinar. However, after that, we will have 5 minutes where I have about 5 more slides. If you just wanted to hang around and see what some of our affordable cameras are, I have a listing of about 4 slides with 4 different models. So we'll talk about that after the question and answering.
Okay. Here's one. I actually could have used this a few years ago. Are there examples of using thermal imaging to detect burrowing pests such as moles, voles, gophers, etc.?
Oh, that's a great question. And I wish the answer was yes. I wish, because where I live, my yard, my garden, my flower beds are constantly under attack by moles and voles. So unfortunately, I've tried it on very cold days where I know I have mole and vole activity, and unfortunately, I was unable to find it. I wish I could say yes to that, but I can't.
Okay. Are there any emissivity concerns while using they just said the IR, but I'm assuming they mean IR camera?
Sure. So emissivity is the ability for an object to emit its infrared radiation respective to a pure black body. The higher the emissivity of a target, the closer to actual temperature that you can measure. So if you're looking at very shiny components, and how do you know if it's a shiny component? If you can see your visible reflection in it, then you probably see an infrared reflection in it as well. There are many workarounds that for emissivity, such as flat black electrical tape, talcum powder, or even cavities. But generally speaking, many of your targets, even if they're shiny, can show, and you will see, temperature differentials. So if there is a hot spot, generally you can see it conduct across, let's say if it's a shiny component and then there's a insulated cable around it, eventually the hot spot will get to the cable and you will see it there. So just be aware if it's copper, if it's stainless steel, if it's aluminum, if it's indoors and it's clean, you might have a bit of a challenge. And that's true of IR spot guns as well. We all work under the same physics. Fortunately, if you're outdoors, you'll have objects that oxidize, get dirty, get dull. Their emissivities go way up, and they become really good targets for an infrared camera.
Okay. What is the typical accuracy of the IR cameras?
All right, so accuracy of IR cameras can be described in a number of ways. The first way is the general design specs that we as manufacturers build. And I would say a majority of infrared cameras have plus or minus 2 degrees or 2%, whichever is greater. So if I'm measuring a 100-degree object, I have a plus or minus 2 degrees, which is 2 degrees. If it's a 500-degree object, it's plus or minus 2%, which would be 10 degrees. So we can measure 510 to 490. But accuracy also comes into play depending on how far away your target you are. If you're 4 feet away, like the spot gun example I showed earlier, you're going to have a poor accuracy on a spot gun, but a really good accuracy with a thermal camera. If I move to 40 or 50 feet away and I use that same infrared camera, I may be back to having poor accuracy because I can't get enough pixels on the target. That's why we as manufacturers offer cameras that have more pixels. So depending on your application, a 19,200 pixel camera could be accurate within 10 feet. If you're looking past 10 feet, you may need a 76,000 pixel array or a 300,000 pixel array or a 786,000 pixel array and or additional telephoto optics that we make as well. So accuracy really depends on how far away from the target you are, its emissivity, and the temperature you're trying to measure.
Okay, can you discuss IR camera calibration?
Okay, so infrared cameras, when we build an infrared camera, every detector is a unique detector, meaning there are no exact detectors alike. So when we get a detector and put it in an infrared camera, we see how it responds to a known temperature source. Once we see how it responds, we calibrate that to react to that temperature in that camera to the intensity that we're seeing. And this is good for 1 year. Once you get your camera, you now are working with a calibrated camera. After a year, we recommend you send it back for calibration. It's not necessary. You can also check your own calibrations. All you need to do is look at a known temperature source. If you feel confident enough to accomplish that, if it measures within the accuracy spec of your camera, you're good to go. If your camera is giving you some false readings, you may want to contact your manufacturer and have them calibrate the camera for you and send it back. So when we get it back, we tend to look at a wide variety of black bodies. We make certain that it measures each black body accurately within the design spec, and if it doesn't, we correct the camera's calibration right there.
Okay, looks like the last question. What are the challenges for maintaining continuity between doing day-on-day comparisons, continuity in camera placements, reduction of data for trending, etc.? And
all right, so that's a good question. So if you're doing trending, it's always beneficial to take an image of your target roughly from the same position that you took the last one. Because if you are looking at a target from different angles, angles can affect temperature measurement. So camera manufacturers like FLIR, we now make trending software that will allow you to analyze images over time, where you can take images over a period of years, compare them, and look for trends in equipment and types and plot them to see if the temperature is rising or staying the same. but it's advantageous to absolutely know the environmental conditions that you are in every time you took a picture, in the placement that you were at when you took the picture, so you can best approximate your image's temperature measurement. Because if you're looking at a target dead on one time and at a 30-degree angle the next time, as you start to get away from perpendicular from your target, you will affect the radiation that's coming into the camera, and you will increase the reflectivity of the background temperature into the camera. So I would recommend talking to Nicole, and she can get the right technical resource at FLIR or anywhere else to help you appreciate the challenge that you're looking at, because we do have software that will make it easier, and we would love to work with you on that to ensure ease of use and acceptance.
Okay, and we also have a certified level 1 thermographer on our sales team. Ben Goodhead is his name, so he's a resource that we can lean on.
Excellent, that's fantastic.
Okay, same gentleman asked for percent of reading. Don't we need to use an absolute temperature scale like Kelvin?
Can you repeat the question again?
For percent of reading, don't we need to use an absolute temperature scale like Kelvin?
I don't believe so. I've been doing this for 17 years, and I've never heard of anyone using Kelvin or over Celsius or Fahrenheit for any type of measurement on their targets. It's whatever the customer feels comfortable with.
Okay. One last question. We'll let this one slide through, and then you can do your review. At what distance is the IR camera typically calibrated at?
They're generally, again, calibration. We talked about calibration earlier with regards to when they calibrate the camera, they do it in a room, and they're about 5 to 10 feet away looking at a black body, so they can get the entire array of the camera on the black body. When we are looking at distance, we are applying either optics or a small portion of those pixels on that target. And when it comes to calibration, distance will affect measurement signal strength from your target. If it's a long wave camera, the transmission from the target to your camera is almost 100%. So the only effect of calibration from distance in a long wave camera is how many pixels you could get on a target. If you happen to have a mid-wave camera, and I showed the chart earlier, mid-wave cameras, there is some atmospheric attenuation based on distance. And the cameras and the software give you the ability to apply humidity and apply distance, which will affect the signal strength coming to the camera, and we can correct for that in software. So to make it real simple, if you have a long wave camera, which 95% to 99% of all handhelds are long wave, all you need to worry about is, do you have the right array size and right optics? If you have a mid-wave camera, now you have to worry about the environmental conditions.
Okay, that's it for the questions. So if you want to go do your review, go ahead.
Okay. All right, everybody. Thank you very much. Like I said, this is going to be real quick. This is not to go in depth in too much of this. You know, the question I ask is, how affordable are infrared cameras? Well, at FLIR, we have 2 models here that are below $1,000. They're the C2 and C3. The C2 is at $499, and the C3 is $699. And the value of these, they're small, they're compact, they're portable, they fit in your breast pocket, they fit in your pants pocket. They're about the size of an iPhone or Android phone. They have a touch screen, and they've got a single bar that will snap both the thermal image and or the visual image as well. You get a 2-hour battery runtime, and these cameras will store over 500 images. What makes the C3 different than the C2? The C3 adds Wi-Fi. There is a FLIR app on the App Store or Google Play Store where you can transfer your images instantaneously from your camera to your smartphone. You can analyze them in your smartphone, and you can email them out in your smartphone. And the last thing the C3 does, it has an auto hotspot, making temperature detection easy. The next level up is the EX platform. That's the E4, E5, E6, and E8. This is a very popular platform because it's an industrial point-and-shoot camera. Wi-Fi is on all these cameras as standard. The pixel array of these cameras is up to 76,800 pixels, and the image sensitivity is as low as 0.06 degrees C. What that means is image sensitivity is indication of how good, how clear that image is. And 0.06 degrees C for the E8 is a very good low noise image. Pricing in this category starts at around $949 and goes up to $2,999, making it a very affordable, professional thermal imaging camera. Just recently, we've upgraded our EXX platform. We've just introduced the E75, 85, and 95. This is a professional style camera with a 4-inch touchscreen. This is a screen that works just like your smartphone. It's instantaneously responsive. The cameras turn on in under 20 seconds, and they have Wi-Fi on all the models, just like I described in the earlier models. The nice thing about these cameras is they have up to 161,000 pixels. They also have the best autofocus in the business, meaning the camera is smart enough to know what your target is, and you can have it autofocus it almost instantaneously. You can turn off the autofocus and use the manual focus if you prefer as well. This is the first camera class that also has interchangeable optics. So you can get a telephoto lens or a wide-angle lens. These cameras run in price from around $7,000 up to $10,000. And in the last slide, this past May, we just introduced the new FLIR T530, 540 camera class. This is our most ergonomic advanced thermal imaging camera on the market. You can rotate the camera head 180 degrees, allowing you to easily see targets above you, below you, and around corners. It has all the same features of the EX E75 through 95, but it adds that ergonomic advantage that makes infrared imaging so much easier if you are looking for a professional thermal imaging camera. Pricing on this camera ranges from around $10,000 to $14,000. So I want to thank everyone on this call today. I appreciate your time. If you have any...
Thanks, Ed, for the presentation. And I wanted to let everyone know on the phone today that we will be sending out, again, slides and the recording of the webinar. And if you have any questions about what Transcat offers as far as thermal imaging cameras from FLIR, please contact us at 800-800-5001 or on the web at transcat.com. You can also email me directly at nvanword@transcat.com. Thanks again for joining us today, and thank you, Ed.
Thank you, Nicole.
All right, take care.